Okay, it's my turn now, right? So okay, hello everybody once again. So I'm Nguyen. I'm actually in Chiang Mai. I'm going to talk about a topic. First is in probabilities, which is really a topic taught in mathematics, not in computer science. However, we will see the connection and why we are talking about probability today. So first of all, this talk is an introduction talk. I have a very specific idea what to do, because I think there are people who know probability, but not quantum probabilities. But there are, I know in Chiang Mai, Chulalongkorn University, people are working also on quantum computing. And this department is mathematics and computer science together. So the topic at the beginning is just like a topic in mathematics, but in fact it is related and useful for both mathematics and computer science. So I put down my slide here so that I will try to make sure that the talk will be in 45 minutes. And I have a 15 minutes for questioning. However, during my talk, I go very slowly because I want to say this, a seminar is useful only if after the seminar, each person has something to take home. You have something, so I will go slowly, and you can interrupt me at any time during my talk to ask questions. The main thing is make sure that some small message can be get through. Okay, so this is the talk is about quantum probabilities. So can I see people? Do anybody raise your hand if you already heard a little bit about quantum probability before? Okay, Professor Songpong, of course. And how about the others? Because that is very important. Okay. In fact, when you give a talk, you need to know the audience. Okay, who are the audience and what they know, and then you can talk specifically about the topic. Okay, how about, so look at, so the topic of today is quantum probabilities. So roughly the outline is very simple. Pedagogically, if you have a new topic to talk about, you have to ask 3 questions before going into technical detail. What is the topic? What is quantum probabilities? And in fact, after that, you have to ask roughly why you need that thing. And only the last thing is the thing that you're really interested in, how to use that thing in application. So here I will go slowly, and you can interrupt me at any time. Okay. So the first thing I want to ask is this. We're talking about probabilities that mostly we know what is probability, but we're talking about something supposedly new. It's called quantum probability, not just classical probabilities. But you will see that it's not new. It's a 100 years old. Okay, so with the emergence of quantum mechanics at the beginning of the last century, I mean around 1900 until 1925, it was discovered that unlike Newton mechanics, which is deterministic, you know that, for example, the second law of Newton, the force is equal to the mass times the acceleration, not the speed. That means the second derivative. So that is the equation. So if you solve that equation by doing 2 times integral, Newton invented everything for you. He invented, we don't have that before him. We don't know what is calculus. We don't know what is derivative. We don't know what is integral. But he had to invent it, all of that by himself, because there's nothing around in the 16th century. But that solving that is deterministic. But quantum mechanics, as I say a few things about it, is intrinsically probabilistic. That means it is random by itself, not because we don't know enough about that. So probabilities show up in science, and the famous philosopher in England, Bertrand Russell, says this. I hope that you will laugh. Probability is very important for science, especially that nobody knows what does that mean. Do we? Well, we know a little bit because Kolmogorov tried to answer that question, and he sat down to do so-called classical probability CP. So we know everything we learn in mathematics, we learn about classical probabilities. Maybe you heard a little bit about quantum probabilities because you read these two books. These are recommended books. Mathematical Foundations of Quantum Mechanics by John von Neumann back in 1955. This is the language for quantum mechanics. That means what is that? That's precisely what you learn. It's called functional analysis. If you study functional analysis and you don't know why, they only explain to you the following. Why it's called functional analysis? We don't talk about point anymore, we talk about function. So a function replaces the place of point in Euclidean space. And that's what we call functional analysis. But I don't know if students will ask, what for? Now you get the answer. It's for quantum mechanics. If you don't, you might not hear about quantum mechanics, but you use quantum mechanics every day. You use your cell phone. Without a quantum mechanics, you don't have a cell phone. You don't have a GPS. All of that. 30% of the product in the US are based on quantum mechanics. Don't forget that. And you might read a little book called The Feynman Lectures in Physics, Volume 3, which is devoted to quantum mechanics. It's very pleasant. You will, if you read the slide that I hand out, you will enjoy the story about quantum mechanics. For example, why the apple fall to the earth, we fall to the earth, but the moon does not fall to the earth, things like that. Now, so the mathematics is essentially motivated mainly from physics. Mathematics is not by itself for physics. So the question is, how and when the notion of probability surfaced? Well, if you think about it, it's all started with something that everybody face in life, seriously or not. It's called risk. Risk of losing money if you invest or gambling, or risk of having an accident. That's the thing that everybody has, faced risk. So first of all, as human or scientists, first thing there are two things to do, counting and measure. If it's a discrete thing, we count. If they are not discrete, like the distance from one place to another place, we measure. We measure geometric thing. But then the question is, did you ever try to measure risk? What is not geometric thing? Or can you quantify it? Is that a number or something? And then measure it? Or you just go out and ask the fortune teller to tell you what is your future. Okay. So what we try to do is try to replace the fortune teller by using probabilities for many things in life. So back in 1494, an Italian monk named Luca Pacioli, he posed the following puzzle to everybody. Suppose that two persons play a best of 5 of dice game. You play 5 times. If you get 3 out of 2, then you win, just like a tennis, just like in grand tennis, a 5 game. Okay. But the situation is, suppose after the first 3 games, one player is leading 2-1, and the game is interrupted and cannot be resumed. Then the question is, what is the fairest way to split the price of that gamble, taking into account the state of the game when it was interrupted? You have any idea? Don't forget, at that time, there's no concept of odds or probability yet. Huh? This is in the 15th century. It took 164 years later This puzzle was fully solved by the two French mathematicians, Blaise Pascal and Pierre de Fermat, in a series of 5-letter exchanges between them in 1654, giving birth to the theory of probabilities. I think that every math student knows what is a Pascal triangle. It's for that game. The solution is simply this. The gambler who was ahead, that means winning 2 out of 1, will prevail. That means will win if 2 game more. 3 times out of 4 if the game is completed, and therefore he should untie the 3/4 of the plot. For example, if the price for the game is 1 million baht, the one who win 2 will get 3 out of 4 if the game is interrupted and cannot be repeated. So I leave that for you to figure out. Now with probability that you know, it will be easy to figure out. But that was how probability is invented. And invented for what? For measuring risk. Quantify risk and measuring it. Okay. So the uncertainty in the game of chance is somewhat, but it's a man-made. That means where the uncertainty come from? Because you make the die. You make the die, not nature. You make the die into 6 faces. And that's what we quantify the probability from man-made. That explain that, but that is useful. That was used to explain the past and predict the future until today. So classical probability is used in variety of applications whenever uncertainty arises. So probability is used as a likelihood or odds for uncertain event. So with respect to risk, can you use that probability to really measure risk? Okay, if you look at, for example, if you quantify the risk of losing money in an investment as a loss random variable X, defined on probabilities by omega AP, and which has distribution f of X. That distribution is equivalent to the law governing the random evolution of X by Lebesgue-Stieltjes theorem. Then a risk measure, what is how much money you might lose in the future, and it's called the value at risk. And it is right now using at the Bank of Thailand or any other bank, using the quantile function, using the pseudo inverse of the distribution function. But that pseudo inverse is not additive, because if you put in the function g alpha equal to this, then the quantile function is an integral with respect to a non-additive measure. And this is not a measure, it is a Choquet integral. It's a Choquet integral, which is non-additive function. That means classical probability cannot be used to quantify risk. Why? Because the risk is not man-made, it's natural. And that analogy with quantum probability is striking. That's what I want to have you an idea about why we have to do that. In 1951, Richard Feynman, the one who got Nobel Prize in quantum mechanics, came to Berkeley to tell the statistician and probability that what you're doing is not what nature is doing. The probability in nature is not additive. That means it's not quantum probabilities. But it doesn't ring the bell. Nobody pay attention. This is 1951. Don't forget that. And now we will say why now everybody are talking about quantum probability. And then we will see what it is. Perhaps the reason that nobody pay attention is the following. We are not physicists. We are mathematicians or computer scientists. So why we worry about something that is so complicated? Okay, and that's why they don't pay attention. The question is, so why now? You will see that nothing is new under the sun. History keeps repeating. A new concept becomes popular only when its time has come. That means when you see why it's useful. This is what the French Victor Hugo said. Nothing is so powerful as an idea whose time has come. So let's evaluate a little bit on quantum probability right now. So at the turn of the century, physicists discovered that physics and mechanics of tiny particles like electron or photon do not follow deterministic law of Newton. And they are intrinsically random. That means they are random by itself, not because that you create like you make a die or a coin. A kind of uncertainty not created by human, but by nature. So an approach to quantification must be different than what we know as classical probabilities. So you know very well the classical probability that you learn in mathematics are based on real analysis. Real analysis are in fact initiated by Newton himself. But the mathematics underlying quantum probability is a functional analysis, as von Neumann laid it down for us. Since the state of an electron or a photon is not a point in the Euclidean space, but it's a function, solution of a complex PDE Schrodinger equation that we will talk about in a few minutes. So the answer to the question, why quantum probability is the following. Because it is uncertainty created by nature governing everything we live in. Okay, so at the remark, differential calculus was developed in mathematics to show Newton's law of motion. When we learn mathematics, we would like to know why and where it comes from, rather than just do and without knowing what for. But solving complex PDE of Schrodinger equation became the main activity for mathematicians in the last century. Because Schrodinger equation, as we will see, is the law of motion of particles. So without going to tell everything about quantum mechanics, you have my extra reading handout that you can read. I hope that you will enjoy it. So the solution of the Schrodinger equation is a complex value function describing the state of an electron. That means electron, everything is moving. Everything is moving. Okay, everything in your body is moving. The question is, at a given time, if you want to know where is that thing, okay, then you have to have an equation. If it's deterministic, you have Newton's second law. If it's quantum mechanics, you are going to have Schrodinger equation. So because of that, everybody was talking about how to solve PDE. So anybody studying a partial differential equation, if you want to solve PDE for the Schrodinger equation, you can use a theory of Feynman for doing this kind of things. So the second question is, what is quantum probability? So as I already said, viewing this talk as a gentle introduction to quantum probability for graduate students in mathematics and computer science for quantum computing, I will proceed to point out that quantum probability is simply an extension of classical probabilities. And that is not surprising because quantum mechanics is generalized. Quantum Newton mechanics is not wrong, but it's only correct for big things. But quantum mechanics is the extension of Newton mechanics to handle mechanics of small things. So probabilities, so quantum classical probability is for Newton, and quantum probability is for quantum mechanics. So it looks like an extension. So how is the extension from classical to that? First of all, before that, this is the recommended text. If you want to know a little more about how to do quantum probabilities, this is a good book that you can get an ebook on Google. In my next seminar on April 27, I will give a favor of mathematical research. So today I only try to show you the following. What is the quantum mechanics? Why we need quantum mechanics? And what is a quantum probabilities space? That's the foundation. Like in probability, what you all you need to know is what is probability space. So what is the quantum probability space? That's what I try to do. So let me, I will show you in half an hour everything from A to Z to show you what is the quantum probabilities. And I hope, my hope is this. You will see that quantum probability will be non-additive and non-commutative. That's the two main things different with classical probabilities. And I hope that if you pay attention, anything you want to know, ask me now, because after this talk, if you go out on to the Long Kong campus and you run into anybody in the street, and if you cannot explain to that person what is quantum probabilities, you don't understand it yourself. That is Einstein, okay? Make sure that you have to explain it simple way that a person in the street can understand. If you cannot do that, you don't understand yourself, the concept. Don't forget that. That is Einstein thing. That's what I learned by myself. All the time, if I learn something and I try to find out someone to explain, if that person cannot understand, I did not understand it well. So I have to go back and learn some more. So first of all, everybody know the basic of classical probability is a probability space consisting of three things. Omega is the sample space. Okay, what you can see, like when you throw a die. Okay, so the die can give you 6 number 1, 2, 3, 4, 6. That is omega. Okay, that's the thing that you can observe. Statistician call that the sample space. A is an event, which is a subset of omega. Okay, if you want to know an odd number, so an odd number is not a number. An odd number has 3 numbers, either 1, 3, or 5. Okay, so the subset of 1, 3, or 5 is an event, is a subset, not a number. Okay, and P is the chance or the probabilities of getting what you observe. Okay, for example, if this is a die, then the probability of getting X number, if the die is fair, is 1/6, things like that. So it's describing the uncertainty affecting our observation. Either in the random experiment, that means man-made, you make the die, or random phenomena is from nature, like nature is the temperature in Bangkok. Okay, the temperature in Bangkok every day is a random phenomenon. You cannot predict that tomorrow, but it's not man-made, it's nature. So first of all, to avoid functional, don't forget, functional analysis will be the basic for study quantum probabilities and quantum mechanics. But at this time, we don't need to use functional analysis. I only use matrix algebra. Okay, so this is undergraduate mathematics. If you have undergraduate mathematics, matrix algebra, you should be able to follow my talk easily. But after that, you will make the connection why we need to extend matrix algebra to functional analysis. So let's take, to be very precise, let's take the sample space omega to be a set of n of points. Okay, if you think about the die, you can think n equals 6, otherwise anything. So you take the event is the power set of omega, that means the set of all subset of omega. And the probability of the event, what is the chance of getting an odd number, is equal to the sum of the probability of getting X number in that set A. That's what, so this is all we know, the three things in probabilities. But when you perform the experiment, you are interested in many different quantities, not only one. If you throw a die, or let's say if you throw 2 dice, then n will be 36. If you go 2 dice, you're interested in what? If you want to gamble, you're interested in getting a sum of 7 or getting a ratio of something. Okay, so X quantity like that is called a random variable, and the random variable depends on the uncertainty in your experiment. That means suppose that is a die. So the random variable is a map. When you toss the coin, it will tell you you can observe what is the value you observe. But if it's random phenomenon, then you can only observe. You don't know what is omega. Okay, omega is like that, but it's hidden. So we will identify a point density, a random variable, x1 with diagonal matrix n cross n matrix with entry in the real line. With respect, of course, in order to talk about matrices or vector, you have to first specify a basis. So the basis will be from 1 to n. Let's say here is the space Rn. And this is the so-called the cat notation of Dirac. Okay, remember, if you have this one together with this one, you get a bracket. A bracket is nothing else than the inner products of a Hilbert space. So half of it on the right, bracket. So this is the cat. The other one is called the bra. Okay, this is the thing that Paul Dirac did that. You might know his famous Dirac function or Dirac measure, but he did much more than that. We will say a few things about him later on. So pedagogically, this is another way to reformulating classical probability. First, I will reformulate classical probability at a special case of quantum probabilities, and then do extension. So first of all, let me identify an event. In classical probability, an event is a subset of the sample space. But a set is equivalent to its indicator function, one sub A. When it's equal to 1, if the element is in A, equal to 0 if it's not in A. Then I can represent that event by this n cross n matrix, diagonal. The diagonal term are the value of the function. So this equal to 0 if 1 is not in A, and this one equal to 1 if number 2 is in A, and so forth. So every event is a diagonal matrix. But if you look at this diagonal matrix, what is it? This diagonal matrix is a projection. It's a linear operator from Rn to Rn. When you multiply a vector to this matrix, you get another vector, and it is linear. So this one, this matrix is a linear operator, linear projector orthogonal on the eigenvalue, and it's symmetric. Two things. This matrix is symmetric and idempotent. Okay, that's why that means you multiply 2 times. That is a prediction. A prediction, an orthogonal prediction. That means if you have a p prediction, p square is equal to p. So roughly, you change the language. So that event in classical probability become a projector, linear projector on Rn, which is a finite dimensional Hilbert space. So we just said, okay, so the set of all events now you equivalent to the collection of on projector on Rn. So an event is a projector. You change the language from one country to another one. Okay. Second one, the probability measure. What is defined in terms of the density. Now you can identify the probability by another n cross n matrix, symmetric, and the diagonal are the value of the density. The density are positive and add up to 1. So this is a symmetric matrix with trace. Sum of their diagonal equal 1. Okay. So what is the probability measure that we change? So a positive probability with trace 1 is the probability in classical set. Okay. That we get 2 things. Now, so also you can see that the matrix F, the density F, can be represented at the vector of Rn. This is the vector, and then you take the square root of n, you take this one. If you take this one, then the norm of this one equal to 1. This is so it's equivalent. That is very important because what is the state of nature that we are in? And that is a vector, unit vector, a vector of unit norm in the space. So that's what I want. Okay, remember here is what I said. This is the inner product of two things. The one on the left, on the right. And if you put together this one on the left, is called the bra. The one on the left is called the cat. So you put together is a bracket. Okay, that's what how Dirac tells us. He has many things, not only that. I will tell him something about this. Okay, so a state. What is the state? It is the probability P in classical logic. Okay, that's what a state is probability logic. So in general, in the context of well, I'm talking about when I move to complex variable, so we are talking about self-adjoint operator in the Hilbert space. So the density matrix rho, which is a positive operator with unit mass, is simply of the form. What is it? This is not an inner product, it's an outer product. It's an outer product. Don't forget the cat is a row vector and the bra column vector, and the bra is a row vector. So when you multiply a row vector with a column vector, you get a matrix. Don't forget that. Okay. So we note right away that given a classical probabilities, you can get the probabilities by the following. The quantum counterpart. What is the quantum probability of A in the new language? It's the trace of the product of the state and the event. You can see if I change Rn to infinite dimensional, there's no integral. There's no more integral. You never have integral in an infinite dimensional space. How you do integral in infinite dimensional space? You replace that by the trace. The trace exists everywhere, finite or infinite dimension, and that's the beautiful thing of functional analysis, to replace real analysis. Now, finally, random variable. What is the language? How you call the random variable now in quantum probabilities? You are going to call it an observable. Rather than say random variable, we will say it is an observable. What does that mean? That we can observe. What is it? You identify the function again by an n cross n symmetric matrix where the diagonal are the value of that quantity. And you go see that the value, even if everything is complex, if the matrix is a self-adjoint, the spectrum, that means the set of all eigenvalue, whereas all the diagonal are all real, because quantity of physics that we're interested in are real value. Even the equation governing them is complex. So an observable is a symmetric. So in general, it's self-adjoint. Self-adjoint or symmetric is the same. Random. What is random variable in quantum probabilities? It is a self-adjoint operator. So we can have everything. Now, shortly, when we extend Rn to Cn, we need to go complex. Anybody want to ask me a little why you need complex number in quantum probabilities? Because the states in quantum mechanics are wave, and wave is represented by complex number. That's why we have a complex number in quantum mechanics. But the main thing for you to appreciate is the following. The trace operator replaces integral. Okay, so one more thing. For example, if you want to see if x is random variable, you know what is the mean, what is the expectation by doing Lebesgue integral. So if you write out x an observable, it's still a random variable, but in a new language. So how we compute the expectation of that random variable? It is equal to what it is here. You can see the trace. Everywhere you think about integral will be a trace. Rho here is the probabilities, and x is the variable itself. And everything here you can see, this is the matrix, this is another matrix. You multiply the two, and you take the sum of the diagonal of the matrix. But you keep thinking about one thing. When you do matrix, if you only look at symmetric matrix, so multiplication of matrix is commutative. But if they are not symmetric, they are not diagonal. If two matrix is diagonal, A and B, so the product of AB equal BA. But if they are only symmetric but not diagonal, the product is non-commutative. And you will see that fit very well with the real thing that they do in quantum mechanics. That's why the formulation of functional analysis fit very well. So in summary, the classical probability space omega AP is reinterpreted as a triple of three things. So here is a classical probability space. Here is a quantum probability space. First, the sample space is replaced by Rn. The set of events is become the set of on projector on this Hilbert space. I talk about Hilbert space because if there is not Hilbert space, you don't have projection. And rho is a self-adjoint with unit trace, or it is an element of this one with unit norm, would be the same. So of course, nothing changed. Diagonal matrix form a commutative sub-algebra of the algebra of all the square and cosine matrices. So all you have to do now is to replace, to extend everything, So for example, a quantum event is a projector, but a projector need not be represented by a diagonal matrix. It can be different. So a quantum event is a projector, whether it is diagonal or not. An observable is a self-adjoint operator. That means it is symmetric but need not be diagonal. And a density matrix is a positive operator with unit trace. But positive operator does not need to be diagonal. A positive operator is just a positive operator. And the norm, the trace is always the sum of diagonal is equal to 1. So you can see we can extend everything into the general term. So finally, a quantum probability space is a triple of three things. H is infinite, complex, infinite dimensional, separable Hilbert space, like L2. Like the space is precisely L2, because L2 we will see in a minute, will be the solution of the Schrodinger equation. P is the set of projector on H. And rho is the density metric, which we call a quantum state, that at every time, a given time t, the moving system of the electron will be in a position. And where is that position? That position we call it rho. That means we call it a state. the states Newton mechanics has a phase space, which is R6. That means where is the position at the time t of a moving object, like an airplane or a tennis ball? Where is that? At a given time, you know the position. You know the position x, y, z in the 3 dimension, and the speed of that one, because it's not fixed. It's moving to that one. So it is in R6. But in quantum mechanics, the position of electron at one given time is not a point. It's not a point. The reason is it is a point, but you cannot see it. That's why. So what is an electron? An electron is a wave if you don't look at it, but it is a particle if you look at it. I think that if you read my handout, everything will be very enjoyable. You don't need to know quantum mechanics. You just need to know a little bit the motivation. So roughly a bit of quantum calculus. So we know now. Any question? We know now what is a quantum. If anybody asks you what is probability, then you say it's a probability space, which has 3 things. Arbitrary space called the sample space. The power set of that sample space is called the set of events. And then a probability P would tell you the chance for X event to happen. That is classical probabilities. Okay. The rest is computation and application. So now the question in quantum probabilities. You want to ask what is quantum probability? So the answer, this is you will explain to anybody you meet this afternoon or tomorrow in the street. Okay. Try to stop anybody and ask you, you want to know what is quantum probability? I will tell you. Okay. You will tell him or her the following. A quantum probability is a triple of 3 things. The first thing is an infinite. Don't say infinite, separable, complex Hilbert space. He will not understand. Okay? You will say it is a space to represent the position of things. Okay? The quantum event is not, it will rain or not. It's not like that. A quantum event is a projector. Try to figure out if that means it's only when you do something to it and you can measure it, that's what you see. That's what we call the famous problem called the Schrodinger cat. If you put a cat in a box and you put next to it a gun and you tear the gun, then the cat dies. But before you open to see if the cat died or not, the cat is not dead. The cat is not alive. The cat is in the superposition of 2 of them. Why if you want to know what happened to him, you have to open to see. If you don't open, you cannot see that the cat is already dead or not. And that is the basic of quantum mechanics. And probability is invented, try to really to describe that situation. So we have the quantum probabilities. Okay, you had a quantum probabilities, and I was a little bit here about how you compute it. Okay, let me show you quickly a little bit what is the Schrodinger equation. Then you can see how you compute. For example, if you want to say what is the chance that you will win when you roll a pair of dice, okay, then you can compute easily. Suppose that you say, if I roll a pair of dice, if I get a sum equals 7, then I win. If the sum is not equal 7, I lose. So before playing, you can compute the chance. If the chance to winning is too small, you don't play. Okay, and easy from the space omega AP. So the question is, how you do that in quantum probabilities? Where is the quantum probability come in to get you know? And that is, I just mentioned, and I think that if you have any course in functional analysis or in matrix analysis, you know what is spectral decomposition. Okay, everything is based on a spectral representation of cell adjoint operator. And that the quantum law, that's what we're talking about. The quantum law, if you have random observable X in the state row, what does that mean? That means you have an electron moving at a given time, T. You want to know where it is. So at that time, T, you are in the state row, and that state row will be provided for you. And you compute the chance. You cannot find where is the point, but you can find out what is the probabilities, and that we will see that the basic for quantum computing. Quantum computing, you cannot have a register of just the bit and write out thing. You have a qubit instead. So a little bit of qubit. Okay, here is the Schrodinger equation. It's only one this. What is a quantum mechanics? What is a normally a Newton mechanics? Only one, right? F equal m velocity and acceleration. Don't forget the following. There's no theorem in mechanics, in physics. There's only equation. Then you don't prove this one. You don't prove this one. This is just come out from whatever you think, and you do testing, and it fit what you observe. So look at this equation. Here, I is a complex number, of course. H is a constant, just like a c, just like a speed of the of light, 300,000 kilometer per second is a constant, and h here is called a Planck thing. And this function phi is the solution of this one. If you solve this equation, you get the function psi of xt. It tells you two things. X is the position, t is the time of that particle. But this doesn't give you the position t. If you take the absolute value square of this function, then you get the probability to find out that thing at the position x. So everything is just this equation for everything from iPhone, GPS, everything, how you send signal, everything is based on this equation. So when you solve this equation, you get the function psi. That it gives you the probability, quantum probabilities, and you apply that to whatever application you're looking at. That's what I put down here. The problem is how to obtain the probabilities. You want to do something, you want to find out something, you cannot just solve an equation and look for it. The maximum you can is to find out the probability for finding such a thing. So the Schrodinger equation tells us that at time t, the object is in the state row, which has the probabilities. It's the absolute value of this. So this one is complex, but when you take the absolute value and square, you get a real number. So solving equation, you can use something called Feynman path integral. So one thing about Dirac that I said, when Schrodinger equation is not a theorem. Richard Feynman put it this way: the equation just came out from the brain of Schrodinger, a young kid of 25 years old in Australia. In physics, unlike mathematics, the most important thing is not a theorem, but an equation. So when meeting Feynman, Paul Dirac asked him only one question. I have an equation. Do you? Let me ask you, everybody. How many equations that Einstein have? I put down here too, you know, right? He have 3. The other equation is the relativity. This equation tells you that mass and energy are equivalent. C is the speed of light. It's constant. This is like exchange rate, just like you change baht to dollar, US dollar. Okay, you take M is a baht, and E is dollar, or the other way, like the other way around. What is it? Like right now, the C is 2. So mass and energy are equivalent. So the light have the light. Does the light have the mass or not? The light from the sun go to you has mass or not? It has energy. It makes you hot, right? It warms you up. So it has energy. But according to this, if it has energy, it has to have mass. Don't you see? Don't you see how they can tell? And okay. And over here you can see energy is equivalent to frequency. That is why you do solar energy. That's why how you use solar energy, how you put a metal piece in the sun to get electricity. It depends on not on the light, but on the frequency of the light. The frequency give energy, not the light itself. Anyway, so let me say one more thing before we can stop. Okay, so I hope that you have you had a following. What is the quantum probability? It's roughly, it's simply a simple form in matrix. It generalized classical probabilities. That. And why we need quantum probabilities? Because we are doing some kind of uncertainty, including risk in finance, that we need something similar to quantum probability to do. So now to the last question, what for? All of that. So of course, you have all that in my big handout. But I can tell you, first of all, quantum computing. You have many people in Chulalongkorn in computer science doing that. And you know why they need that to do. Because quantum computing will be faster and for optimization, anything. So quantum computing, in fact, is the main activities using quantum probability in that right now. And in very soon, we will have a quantum computer. And then also in econometric or in statistics, you can see that we have so many things all put together: economic statistics, decision theory, social, and then of course machine learning. It's all because econometric, decision theory, social, they involve human. So human risk is not for something. Risk is because the risk of human. All that aspect depend on another kind of uncertainty that cannot be modeled by classical probabilities, but only for quantum probability. So that all these 3 things you can see, quantum probability, economic, decision theory, machine learning, all of that right now is a very active research thing. So that's all I have to say for today. But I do hope that you got something to take home. You come home, Ajahn, teacher that if you have whatever, your young brother or sister, you can come home, and if they ask you, what do you learn today, and you say quantum probability, and they say, what's that? You should be able to explain, and they should understand in simple terms. No quantum thing, but they say, oh, that makes sense. That makes sense. You know, this. I don't know how to fortune teller or something. I eat fortune teller, but if we do it scientifically, we should do somehow compatible with whatever. So in my next seminar, I will go into more detail. I already sent it out, and so we can see how the mathematics is doing and what are the, for application is many, especially in computer science and machine learning. Okay, that try to understand and apply. But if you ask the question, what are, for mathematician, what are the things we can do with probabilities? You can see I did not mention one thing here, very important. Conditional probabilities, is that what they do for application with classical probabilities. So I would address the research problem in mathematics and some result based on conditional quantum probability next week. Okay, so I think I just on time, but we can have a 15 minutes for questions.
Thank you very much. Are there any questions?
You should have a question. I think that if you don't have a question, that means you understand everything. Okay, so make sure that you ask question. There, I really want to listen to a seminar, because when someone talk on seminar, I will have at least 15 questions. No, so is there anything that you want to know? For example, if we want to talk about mathematics, what do we need to study or do research? If you want to help people doing quantum computing, what do you need?
There is a question in the chat.
Okay, could you say it? I don't see it. Oh, you mean there's, I see it. I should click on the chat.
Yes,
okay,
yes.
Question. Okay, question from audience. The first one is, okay, good. What is the meaning of von Neumann entropy? Okay, and what are the situation use entropy to measure uncertainty? Okay, I answer. Don't get anything. First of all, when you ask a question, you ask a question about what I'm talking about, not anything outside. Okay, when we talk about someone talking about it, because we're talking, I did not mention entropy, but I know, so I can answer you. Okay, but in general, when you ask a question to someone who give a talk, you ask about what they are talking about, not anything outside. Okay, so classical entropy. If you write down classical entropy, what's that? Integral minus integral f of x log of x dx. Can you translate that to quantum? That's what is von Neumann. Integral replaced by trace. Okay, integral replaced by trace, and the f is the density, is replaced by rho. So if the trace for Neumann entropy is equal to the trace of the state time log of that one, of rho, because it is log of the thing. And that is the answer to what is the meaning of entropy. The meaning of entropy is the same meaning as in thermodynamics. What is the entropy in thermodynamics, in the classical one? The entropy is the represent the disorder of a system. That's the meaning of classical entropy. So for Neumann entropy had the same meaning, but for quantum system. Okay, and you ask, and which situation will you entropy measure to measure a certainty of event? The entropy is not the uncertainty of the event. If you want to measure uncertainty event, you use probability. You don't use entropy. Entropy is not a measure of uncertainty. Entropy roughly is a measure of equilibrium, but not of uncertainty. You cannot just, because you can see you can see the entropy come out from probabilities. You need to have probability in order to define entropy. Okay, so there are two different things. It's related, but you need probabilities. The entropy of the thing, if you go back to the origin of entropy in thermodynamics, that is when the system gets to equilibrium. The entropy represents the measure of disorder in a system. And the second law of thermodynamics said the following: systems tend to go to the maximum disorder. And that's what they call the equilibrium of that time. So entropy can be used, but it's not, if you say, and how, which situation we use entropy to measure the uncertainty of the event. The uncertainty of an event is always measured by probabilities. Okay, you answer that one, chat. Is that okay for people to ask that question? You say one more? Okay. Okay. Can you advise some basic book to follow this work? Okay, already there. Okay. First of all, if you want to follow this book, I don't know, Ajahn, did you forward everything?
Yes, I sent the link to the chat.
Okay, so it's a very easy. Number one, if you want to enjoy a little more, enjoy, not have had it, then you read my additional reading in there to have a little bit. After that, if you want to do it, you can see, remember that I recommend one book, right? I recommend one book. Where is that? I recommend one book from Parathi. But okay, you can see in here, you can, let me see, did I, here is the book. Where is, I think I put down a book, right? No, it's in here. Okay, you can see the book, but let me tell you this, the easy way for everybody to learn things now. Okay, here the book. Okay, here is the book. Okay, Introduction to Quantum Stochastic Calculus. This is a good book to learn. Okay, but I tell you another one. Google. Nowadays, you know, when I was student, there's no computer yet. Don't forget that. I studied in France in 1970. Okay, there's no even wireless phone yet. Okay, there's nothing. But nowadays, the best way to work, what you want to learn, you want to know what is quantum probability, type it on Google. There are thousands of lectures from good professors to read anything. If you want to know, what is quantum entropy, type it on Google. You get it right away, but make sure that you print it out and read, rather than read right away on that. You don't get anything. You have to print it out and read. Okay. So for this question, this question? Okay. Something else. The slide and additional thing can be downloaded. Okay, you do that to anybody. Yeah. So if you by some reason you cannot that, you simply, I have my email on everything. You can send me. I will be glad to send if you have any problem.
There's another question before my message.
Okay. From the definition of why do we need? I don't have the whole sentence. Could you?
Why do we need the condition of rho to be with unit trace?
Oh, okay. What is the probabilities in general? A probability in classical probability is a measure with probability equal 1. 1 is 100%. Okay, 1 is 100%. The biggest value is 1 in probabilities. Okay, 100%. So when you translate quantum probability into the quantum mechanics language, it is also a probability. Quantum probability, the meaning, quantum probability and ordinary are the same. What is different? The way to do calculation. Only the way to do calculation. It's still the chance. It's still the chance of getting something. What is the chance of winning lottery? Okay? You quantum probabilities, you classical, because it's man-made. Who made the lottery? Man-made made lottery. So do you quantum probability, classical probability? The trace is equal to the total probabilities. So the trace equal 1, or the norm of the vector equal 1, that is the counterpart of probability equal of the whole thing. Sure is 100%. That means 1. Okay. Definition of quantum probability, of course. A quantum probability is the same as an ordinary probability. That means the total mass is equal to 1. Okay. The total mass in quantum probability is computed by computing the trace of that density matrix. Okay. What is different between the two is that the calculus is different. For example, two things is not additive. Probability of A union B is not equal to the sum. Probability of A intersection B is not the same as intersection of B intersection A. It's not commutative. Why? Because that is exactly what we observe in physics. It's not invented by mathematicians. That is what the physicists observe and tell us, could you provide for us a language to do calculation? Just like Newton invented calculus and differential equation, differential calculus to do classical mechanics, then you know how to make an airplane. If he know the rule for the thing to fly, but you need to have a language in order to solve and compute many things in order to make an airplane. Even you write out, he write out the equation. He write out equation. It has no math. The equation is only this. The force applied on something is proportional to the mass of that thing and the acceleration of that thing. That's what he learned from Galileo. But no math. So the question is, you say things like that is a qualitative. So in order to make the airplane, you cannot just say, how much the mass and what is acceleration on that? How can you do it? You need a language to write down, to quantify that. So you need something called F, the force, equal that mathematics, M, the mass, time, second derivative. That is acceleration. Where is derivative? Nobody knows what is derivative at that time. Newton had to invent it. And after that, how you get the position? How you get x? F equal m d square xt over dt square. So how you get xt? You have to take integral one side, then you get the derivative. You take one more time integral, and then you get the function xt. On that need integral, calculus, integral, and differential calculus, and Newton invented on by himself. Okay, not only he see things, but he invented all of that. Now we are very lucky. After that, when quantum mechanics how and they say, the equation is not the same anymore. Okay, it's not the same. So, but we don't know which equation. We don't know which equation. Okay, Schrödinger came out and gave us the equation. It turned out it fit well, just like Newton have his first law. But the question next is this: what is the mathematics to solve that equation? Schrödinger did not invent it. Von Neumann invented it. Okay, that's why if you are a mathematician, you will say the following about von Neumann. There are two kinds of mathematicians: John von Neumann and the rest of us. Okay. Okay. One good thing about Newton. How you say good thing about Newton? Million people see the apple fall from the tree, but he is the only guy who asks why. And how about Einstein? When Einstein was 16 years old, he asked the following question: what do you see if you can run fast like the speed of light? And that everything is from that equation, from that idea that he get. He invented quantum mechanics. Okay, don't forget that. But he doesn't like it. That's why he go into relativity. He doesn't like it because he doesn't like the fact that things happen in nature at random, not man-made. Nature make things random. He doesn't like that idea. That's what he said. He does not think God played with dice. He doesn't think. He doesn't like that. He doesn't think that that thing. He thinks that everything is well organized in nature, not at random. So he go in and do something else. Okay. In fact, he was the one. Or anything? Any other questions? I like a question. Okay, because I know that you have some interest.
Do you have time for one more question in the chat?
Otherwise, don't worry. Think about, read again, put down all questions, and you can ask me next time. Okay, another time. So don't worry. And anything, the thing is this. This is 100 years old, not yesterday. Okay, but I explained very well. It's so important. That's why you have a GPS, you have your iPhone, you have everything. It's from quantum mechanics. Okay, but they say, okay, that enough. That enough. Engineer can do things around and get that for us. It's fine. Okay, and so why we have to study quantum probabilities? Okay, it even probabilities did not learn this long time ago, because now the main thing is computer science. They are going to have a new computer, quantum computer, and that's why they turn to quantum probabilities, because everything inside is probabilities. That I will talk a little bit next time. And therefore, and after that, there's many things that fit very well with this. That's why mathematicians started doing research 100 years after it was invented. But you will see, you have everything. You have everything ready to study this, because that is called functional analysis. When you study functional analysis in mathematics, I don't think that the teacher tell you why you learned in this and where it come from. It come from quantum mechanics, quantum probabilities. Okay, so you already had on the thing hit it. You just need to appreciate and have a good feeling about what is probabilities. The thing for me is very simple. We're talking about doing the old thing. We're talking about how you assess the risk of something. Okay, in every situation, insurance company, electronics, everything. we need to know how to compute the probability to change for that thing. Okay, now the same problem, but we have other situation. The classical is not appropriate anymore. Okay,